let an be the number of non-negative integer solutions to this system here, x1 plus x2 plus x3, and they have to be non-negative integer solutions, but they also have to have the following constraints. So x1 has to be even, x2 has to be at most 2, and x3 is a non-negative integer. So this one actually has no constraint. Okay, so let's look at how we can encode this into a power series. So the even, we can encode this as the following power series. We just get, so of course, x to the power of 0, which is 1, is even the 0, and then x squared, x4, x6, and so on. At most 2, we can just put x to the 0, x to the 1, and x squared. And here, no restriction, so any of them, well, it's just no restriction. So it's all the powers of x here, right? Okay, and once again, what are we interested in? We want to find, so our a of x is just multiply all of these, right? X squared plus x to the 4. And we multiply this with the second one, x plus x squared, and multiply this with the third one, and so on. And the idea is that this is going to give us some infinite polynomial, some power series. And we are interested in what is an. We are interested in that. Okay. As before, you can just simplify these using a geometric series and finite series. So x1 being an even number, this was the power series. And if you apply the geometric series to this, you get this over here. At most 2 was this, and this is already simplified already, so we don't need to worry too much about it. And this, the one with no constraint, again, by the geometric series, you get this. So what this means is that our a of x is going to be just the power of these 3 things here. And then 1 plus x squared. And then 1 over 1 minus x. And let's say if we simplify, we get a of x equal to 1 plus x squared divided by 1 minus x squared, 1 minus x. And now the issue now is, how do we deal with this, right? And so we would like to sort of break this up into functions that we already know how to get, like, what are they the generating functions of. And so if we could break it into things that are more, ideally, if we could break it into a bunch of things that look like geometric series and stuff like that, this could help us. And one tool for that is something called partial fraction decomposition. So partial fraction decomposition is something that you probably saw in some of your calculus courses when you were doing integrals. So when you were doing integrals, you sort of had this issue also, that you would end up with things like this and you would want to break them into simpler stuff. And so please go check again how to do that. And we also have, if you go to the slides, there's going to be a slide talking about the general version of this. So please go and take a look. Now for this example, so here we're interested, let me copy this here. We're interested in this a of x. And what we can do is we can find constants such that this is going to be equal to a over 1 minus x plus b 1 minus x squared plus c 1 plus x. And here, when you solve this, you get a equal to minus 3 over 4, b equal to 3 halves, and c equal to 1 quarter, which is to say that a of x, you can write it as minus 3 quarters times 1 over 1 minus x plus 3 halves times 1 over 1 minus x squared plus 1 quarter times 1 over 1 plus x. Okay, and now the idea is that for these terms, we actually know how to deal with them in terms of, we know these generating functions for these. So I'll copy this for later, but so we know the generating functions for these. So recall, so we know that 1 minus x is just this summation of xn, so this is the geometric series. We know that 1 over 1 minus x squared, so we had 2 videos where we actually found what this is the generating function of. It's going to be of n plus 1 x to the n larger or equal than 0. So this one we found by, we showed 2 ways of doing it in a previous video. So one of them was doing convolution, multiplying this twice and then doing convolution. And the other one was actually taking the derivative of this. So you take the derivative on both sides and you actually get this. And then actually if you apply the geometric series here and you replace x with minus x, you get 1 over 1 plus x is going to be equal to the summation n larger or equal than 0 minus 1 to the n x to the n. So this one you obtain just from replacing x here with minus x. Okay. Now we have our expression for a of x, and we can now replace each one of these here. And so what we'll obtain is that a of x is going to be equal to the summation of minus 3 quarters, and this one here is just x to the n, plus 3 halves n plus 1 x to the n plus 1 quarter minus 1 to the n x to the n, which if you write it out, if you put all the terms together, this just gives you minus 3 over 4 plus 3 halves n plus 1 plus 1 quarter minus 1 to the n x to the n. And again, we are interested in what is the term of the power n here, so it's just this here. And so that means that our an, what we are interested in, the answer to our question, is going to be this, minus 3 quarters plus 3 over 2 n plus 1 plus minus 1 to the n over 4, which you can also simplify. Let me put some space here. You can simplify this to 3 halves of n plus 3 plus minus 1 to the n over 4. So how many solutions to this equation here, non-negative integers, satisfying that this one has to be even, the second one at most 2, and the third one no restriction, it's going to be given by this formula here.